All right, next up, we've got sp2 hybridization. This one's going to introduce some new ideas, which will actually be useful for us. And it's going to introduce the idea of sigma, which gets the sigma symbol, and then pi, which gets the pi symbol, bonds. So we've got different kinds of bonds, sigma and pi bonds. For example, in H2, we have the overlap of the two 1s orbitals, and then the electrons are in there. Whenever you have this kind of direct overlap where the orbitals are actually overlapping with one another, that's what's known as a sigma bond. And again, this is just a sigma, lowercase sigma, from Latin language, whatever. So for example, CH4, we have direct overlap in all four of these bonds, so we have 4 sigma bonds here. Let's take a look at another molecule. This is formaldehyde. And so we can see that this central carbon now is only attached to 3 things. And so that's going to be sp3 hybridization. So again, you just count the number of things it's attached, and that's how many orbitals are going to mix together. Since we've got 3 things, only 3 orbitals will match or will hybridize. So sp2, that's going to give us this trigonal planar shape. And then let's take a look at what's going on, right? We've got the 2s orbital and then the 2p orbital of carbon. 4 electrons for carbon. We're going to have these 4 orbitals mix and hybridize. And then this leftover p orbital, it's just going to be leftover. So these 3 mix into 3 sp2 orbitals. And then we have 1 leftover p orbital. Each one of them gets 1 electron each. The sp2 orbitals look pretty similar to the sp3 orbitals, except there's only really 3 of them. And they're all in the same plane because we have that trigonal planar shape. And then we'll have a leftover p orbital. Let's color this in yellow, color this in blue. So again, the molecule that we're going to take a look at is formaldehyde. And we're going to take a look at the bonding here. So we've got our carbon. This carbon has 3 sp2 orbitals. So it's got 1 like this. It's got 1 going into the back of the board, and then 1 kind of coming out of the board. Each one of these have 1 electron. And then we've got a leftover p orbital. We'll draw like this. We'll keep that one in the plane of the board, and it has 1 electron. We're attached to 2 hydrogens. So these hydrogens with their 1s orbital are going to form sigma bonds with the sp2 orbitals of carbon. On the other side, we've got oxygen, which is also going to adopt an sp2 hybridized shape. So we're going to have direct bond overlap there, a little bit closer, and form a sigma bond with oxygen. The other sp2 orbitals of oxygen will house its lone pairs. And then it too, so we'll label these sp2, sp2, sp2. And then it too will have 1 leftover p orbital. And then what we can see is in order to form this pi bond, it's not a direct overlap, but these 2 p orbitals are going to bond to one another. So we're going to have an indirect overlap, and that's what compromises our pi bonds. So when we take a look at the molecule of formaldehyde up here, what we have here are 3 sigma bonds. And then 1 pi bond. And here's just a nicer version of one of the sp2 hybridized molecules. In this case, this is ethene. So there's the hybridization, the valence bond theory. Look at it. And then if you think about the Lewis structure, it looks simply like this. And what we can see is that we have 1, 2, 3, 4, 5 sigma bonds, right, denoted by all of these direct overlaps. And you can see it's labeling all your sigma bonds down right here. And then we have 1 pi bond, which is shown as this indirect overlap. Also, nicer picture here in the bottom right. Cool. So what does that tell us new about molecules? Well, it tells us that sigma bonds, they can rotate. Because if you think about these molecules, if this bond were to rotate, we still have direct overlap. We're not breaking the bond or anything just because these molecules are rotating. With pi bonds, they can't rotate. Because if they did try to rotate, the pi bond would break. Right, if you think about the indirect overlap here, if you start trying to rotate one of these carbons, you're going to be breaking that pi bond. And then here's just a nicer picture of that. Here, we have all sigma bonds, and so we're free to rotate about this bond. Here we have a pi bond being formed, right? You can see the pi bond right there. And so now we're not free to do that rotation. And so what that means, for example, is that when we draw the Lewis structure of these two compounds, you can see I put the chlorines on different sides of one another, but we have free rotation about this bond. And so what that means is that these two are the same molecule. Right, all the bonds are free to rotate. However, when we take a look at the analog with the double bond or the pi bond, these two compounds are different molecules. And they're different molecules because this pi bond can't rotate. So there's no way to make this molecule into the other one. This one right here, think about it as like an open fist or a closed fist, or, you take your, hand and just rotate a little bit. It's still the same thing. It's just in a slightly different orientation. These two are completely different things. You can think about it as like kind of a left hand or right hand type of situation. So you can see with the introduction of hybridization, we can explain pi bonds, which can help us explain whether molecules are free to rotate or not.